Hello everyone, this is Professor Jeff Wilkerson at Luther College with a little brief introduction to Exercise 9 from Astronomers as Observers and Experimenters, published by Kendall Hunt. This exercise is all about trigonometric parallax and measuring trigonometric parallax, and there are a few things we want to think about related to that. First and foremost, trigonometric parallax is one of the most important measurements in the history of astronomy. It's one of the most important things we can measure. It gives us the first rung on the cosmic distance ladder. So doing a better job of measuring parallax of nearby objects allows us to recalculate the distances to all more distant objects. And so it really is critically important to do the very best job we possibly can measuring trigonometric parallax so that we can then do a better job of measuring distances to other things. But it's not all about measuring distances. Knowing the distances to the nearby stars really helps us understand stellar modeling that way that we can apply to all these other stars. So it feeds into everything else that's going on here. And so, we want to practice this. This is a great activity to practice, and we will look at this and we'll say, there's the Earth. The diagrams are in your book. I don't really need to reproduce these diagrams, but to say, there's the sun, and as the Earth orbits the sun 6 months apart, there's a star out here, and we can measure that star against more distant stars and to see how much it shifts back and forth. And so we get this parallax angle right there. That is the angle, and we've got half of the Earth's orbital semi-major axis right here that we're looking at to say, okay, that's the baseline. We call that the baseline. We call that the parallax angle right there, P, and measuring that shift. We're measuring this against more distant stars that presumably aren't shifting around enough to be meaningful at all. And so this was such an important, one of the things we talk about in the text is we talk about why, what the purpose is of what it is we hope to learn and do and how it's changing our physical models. So we're thinking about these exercises as making observations, doing experiments, learning from those observations and experiments that allows us to build a model of some physical system. We can go in and we can say, this is how this works, or this is what we know about this thing or the other thing. And so this is a great example of one of the types of measurements where you can imagine that the purpose, the model that we're trying to build has changed as a result, as time has gone on, because it took us so long to measure the parallax, the trigonometric parallax to the nearest star. It took us a very, very long time. I'm going to look to see someplace here. Yeah, I got a copy of this book. I've got many copies around. I was hoping there was one available within camera shot. This Parallax, The Race to Measure the Cosmos by Alan W. Hirschfeld. I'm sure I recommended it in the written text right there, and I'm recommending it to you again right now. It's just a fantastic book that talks about our efforts to measure this trigonometric parallax, and he does a beautiful job of describing that work. And so when we start to say, immediately we can say one of the parts of the process of science that we've laid out in the textbook, in the lab book, is to say that one of the things we want to do is that when you make a physical model, you make a physical understanding of some component of the universe, it is a good scientific model if it makes a specific prediction that can be tested by observation. And then you test it with that observation, and that test will then will cause you to need to refine that model, or you'll say, well, it's consistent with that model. As I'm sure we've said many times before, if you've watched some of these video introductions, we don't ever prove anything is right. We just say the observation we made is consistent with what that model would have predicted. And we move on and we continue to attempt to falsify that model, perhaps. So if you believe that the Copernican Keplerian model of the universe, of the solar system, is correct, that the Earth is actually zipping around through space and orbiting the sun this way, then these nearby stars should be moving relative to the more distant stars, jumping back and forth. Now, it's important, a few things are important to note right there. This star has to be nearby if all the stars are at the same distance, they're all jumping back and forth the same amount, and you're not going to see this. So you have to have a change. You have to have stars spread through the volume of space. That's one thing we're assuming when we look at this. Another thing we have to keep in mind in your application is you need to be looking at this star right here. If you're using this as your baseline, that star has to be right there. It doesn't do us any good to look at a star that's over there as we go from here to here. As we go from here to here, it would, you see. So you need what we're saying is you need that baseline to be perpendicular to the line segment connecting the sun to the star. Okay, and you're going to want that in the exercise that you're doing here, exercise 9. You're going to want the work you're going to do here. You're going to want this to keep that in mind. And so this is really important. As we started to say, when we started to try to measure this, what we were trying to do, one of the primary purposes, there's never, I won't say never, but rarely maybe there's one purpose, there's one thing. There could be multiple reasons for doing an experiment and making an observation and many different things you hope to try to know a little bit better or do a little bit better at, not just one big new thing you're trying to figure out. But one of the big new things we were trying to figure out would have been, can we provide support for the Copernican Keplerian model of the solar system with the Earth in motion by seeing foreground stars shift against background stars? As the centuries unfolded and we weren't able to detect that, because the foreground stars are so distant that this parallax angle becomes so small that we can't really it's a delicious technical challenge to try to measure that shifting, that parallax angle. And as the centuries unfold, by the time we're able to do that, there can just no longer be any doubt that the Keplerian model of the solar system is far superior to the Ptolemaic model of the solar system. So we can't, this is no longer the purpose of what we're trying to do here with this. It's not the primary purpose of what's going on. What we are trying to do instead is we are trying to do other things, right? We're just trying to make this measurement. We're just trying to show that this measurement is going to work, and we're able to do this measurement, but then it also becomes the distance measuring tool that allows us to measure the nearby stars and the distances to those to set the cosmic distance ladder that we're talking about to help us understand the modeling of those stars. So if we know the distance to that star, then we know the luminosity of that star. If we know the luminosity of that star, for example, we can relate the luminosity of that star to the mass of that star. If that star is in a binary system and we can determine the mass, then we can do that kind of work that allows us to do stellar modeling. So this is, you can see how the purpose of this, in terms of the scientific process that we've laid out, you can see how the purpose of this measurement has changed over time as the work has unfolded. So anyway, that's one of the reasons that this is such important work. And it's important work just for you to be able to get a feel for what's going on. So in this exercise, what you're going to do is you're going to look at a foreground object, maybe another person in your lab group, measured against a background object. And you're going to make this. So you're going to pace off a baseline, and you're going to measure how a foreground object moves relative to a background object, and you're going to measure that angle, the effective parallax angle. You're going to know that distance. You're going to measure that distance. Then we're going to ask you to measure that distance directly. So measure how far away this person was that you were measuring the distance to, and you've got two measurements you've made. We're going to call that the direct distance measurement, and we're going to call that the parallax distance measurement. And so you do this, if you're working in a group with 2 or 3 other people, everybody do this. Everybody make this measurement. Pace off a baseline. Try different baselines and try different distances out here. We've made recommendations in the book for what the distances should be, but you can choose your own distances to this distant object, and you can pace this back off and make those distance measurements. And we'd like to calculate the ratio of those things. What is the parallax distance divided by the direct distance measurement? If we're measuring the distance, both of these perfectly, that should be 1, right? You should get the same distance both times, and do you? And it doesn't depend on how far away this object is. If the object is closer or if the object is further, how does this ratio vary as you do this? So we want you to do this. Make a couple of different distance measurements. If you got time, make 3 or 4 different distance measurements the object 3 or 4 different distances away, and do this kind of calculation and see, does this ratio, how close to 1 is it? And is it always bigger than 1, or is it always smaller than 1? And does it seem to depend on the distance this object is away from you? Is the ratio bigger if it's closer? Is the ratio bigger if it's further away? What can you say about that? And to think about biases that are built into these observations. We've talked about this before. So what kind of bias is built in that might affect the parallax distance observations that you're making right here? I'd like for you to also think about a bias that could conceivably be built in. What if your baseline isn't perpendicular? What if you don't have that right angle right there? What if your baseline's tilted just a little bit relative to this object? Does it matter? By measuring on both sides, as we're doing here in this exercise today that you're doing, by measuring on both sides, does it correct for that or does it not correct for that? Why do you measure on both sides? What does that do for you by measuring the parallax angle over here and measuring the parallax angle over here? What does that maybe help you? What sort of bias or error or uncertainty does that help you take out of your measurements or correct for in your measurements? And what can it not do? So what if this baseline is tilted? Are you going to always overestimate the distance? Are you going to always underestimate the distance, or does it not matter? What if this object is closer or further away relative to this distant object? Does it matter where that distant object is? Are you going to always overestimate the distance, underestimate the distance, or does it not matter, or does it vary around? And think about that. And one way to get into that, thinking about those things, is to look at this ratio for all of these different distance measurements. And if you're doing this with a large group of people in a lab setting, where a lot of people have made a lot of different distance measurements, you can write all of this data on the board, or you can share all this data in a sheet on a shared drive or something like that. You can get all of this data shared with each other and look at what not only measurements you made and the people in your group made, but what all the other groups did as well. And maybe you could share it for years. Maybe there's people who've been taking the astronomy course you're taking for the last 10 years and you've been saving that data, or maybe now's the time to start saving that data. And you can save that data over years and years and years and see, get a lot of data to see, is it really, is this ratio always trending a certain direction, always doing a certain kind of thing, to help get a handle on what kind of problems can creep into measurements like this. But measuring this parallax is really important for us. I think this is an activity that I do. Not sure that I've ever taught this course, the introductory astronomy course, without doing this particular exercise. This is one of the key fundamental exercises that we do, because it gives you a feel for this kind of measurement, how you take a measurement of a parallax angle and turn it into a distance that is so important in the astronomical world, that is so critical to our understanding of all sorts of things, as I've tried to imply right here, or just flat out state. So important to our modeling of stellar systems, so important to our understanding of distances, which then tells us about galaxies and so on. There really isn't anything that the parallax measurements don't directly feed. And so this is why I consider this such a key activity to do. Good luck with it. I hope it goes well for you, and we'll talk to you about other exercises at other times. Take care, everyone.